Today's geometry notes we'll use in class 43. Our focus today is going to be the triangle proportionality theorem, which is something related to the similar triangles that we talked about in class 42. So this review and explore section up top, before you get to the boxes, is actually a review of a problem that we learned how to solve in class 42. So I would suggest that you go ahead and pause the video, try to track down your X, your Y, and your W, and then meet me back here to check your answers to make sure that you've got the triangle similarity process, solving process, down. I'll meet you back here in just a few minutes. All right, welcome back. I'm going to set this problem up the same way that I did in the in class 42 video. If your teacher sets things up slightly differently, that's okay. It should all pan out at the end, but this might be something that helps you understand a little bit better or just shows you a different way of thinking about these problems. I always take my similarity statement and I compare the first triangle to the second triangle. And so as I was looking at triangle ASP, that big triangle in the picture, I noticed that side AS and side SP were both variable focused, but AP was a number. And so my goal was to find the scale factor by comparing AP to HE. HE was also a number, so that allowed me to set up my ratio of 56/20. Now, officially, you could use that for all of your calculations, but to be the scale factor, it needs to be reduced. So if we divide both of these by 4, we get the scale factor of 14/5. I'm going to use that official scale factor in my algebra, but again, if you had 56/20, your numbers will just be larger, but you'll end up with the same values for X and Y and W. I focused on X first, so I grabbed my scale factor, 14/5, which meant I was comparing triangle ASP to triangle HSE, and then I went back and I looked at side AS, the first two letters. That allowed me to use segment addition postulate, or required me to use segment addition postulate to talk about, because I needed to add X and 18 together to talk about how long side AS was. That becomes the numerator. That matches up with side HS, which is X for the denominator, and then cross products and solving led me to X equal to 10. Remember, when you have a plus or a minus sign, you're going to do some distributing, so 5 times X, but also 5 times positive 18 is where that 5X plus 90 comes from. Repeating that process, use the scale factor again. Another side from triangle ASP would have been side SP. That was labeled with a Y, so that's my numerator. And then SP corresponds to SE, which is 5. Now you can absolutely still solve this with cross products. That's what I did here. However, if the denominators match, the numerators have to match as well. So it's okay to just look at that and say, oh, well, Y has to be 14, because that's what would make those two ratios the same. Now I have not taken care of W yet, because W is strange. EP is not part of the first triangle, it's not part of the second triangle's name, it's something that's kind of in between. So what we need to do is we need to think about how Y is equal to 14. So this is segment addition postulate here. 5 plus W would need to equal 14. The two small parts of that segment add up to be the whole segment. So we can find W just by using our segment addition postulate all the way from the first standard of the year. All right, hopefully that went well. Otherwise, make sure that you're asking your teacher good questions about in class 42 and maybe doing some extra homework practice or coming into RTI. Moving into today's topic, the triangle proportionality theorem, we're going to investigate this picture a little bit more. And we're going to do that by evaluating a few proportions to see if they are true or false. So, taking a look at what we just found out, SE is going to be equal to 5 according to that diagram. So we're going to plug that in. And then SP, we found out, was 14. Our goal is to decide, so I'm going to put a question mark above that equal sign because we don't actually know they're equal yet, whether that is the same as the ratio of these two segments. HE is 20 and AP is 56. Now, there are lots of ways you can decide whether or not those are equal. We should probably already know they're equal because that's just the upside down version of what I did up here for my scale factor. But you could reduce this fraction to see if it matches, 5/14, or you could do cross products to see if those cross products are equal. Whatever you choose to do is fine, but you will find out that they are equal, which makes this a true proportion. All right, moving on to B, we're going to do the same type of deal where we plug in our values and we see what happens. So if I'm looking at segment SH, that has an X on it, but remember our X is equal to 10, so I can put 10 in that numerator. HA is labeled as 18, and my goal is to decide whether or not that's equal to HE again, 20, compared to AP, 56. So again, whatever you do, whether it's reducing this side would be 5/9 if you divide both of them by 2. This side is 5/14 if you divide both of them by 4. Or doing cross products to see if they're equal. 560 and 360 are not equal, so this is a false proportion, not equal. All right, one more of these. SE. SE is 5. EP is that W we solved for, which was 9. And we're trying to test whether or not that's equal to SH, which was X or 10, compared to HA, which is 18. 5/9 is already reduced. If we divide both of these by 2, it equals 5/9, or cross products would both be 90, so this is a true proportion. All right, so why did we do all of that? Well, we're going to try to decide what it was we were actually looking at, and this will be a little bit tricky if you're just watching the screen, so you're going to have to use the picture at the top of your page a little bit. Our goal is to investigate these three proportions that we just looked at and to see what we were really comparing. So the first one is done for us, but let's make sure we understand what they've done. They went back to the picture and they looked at SE, and they said that was a small triangle side. So when you look at SE in the picture, sure enough, that's a side of the small triangle up in that review and explore diagram we've been using. If you look at SP, that's a side of the larger triangle, and it's a corresponding side. The other two segments that we looked at, HE and AP, are exactly the same, just different sides. So HE is the bottom side of that small triangle, and then AP is the bottom side of that large triangle. So that is what we were comparing on both sides of that proportion. We're going to fill in B the same way. So go back up to your picture, look at SH. Do you agree that that would be a small triangle side? The left side of that small triangle. HA is not the side of a triangle. I'm going to go ahead and slide up there so we can see it together. HA is right here. It's a side of this like trapezoid-like shape, but it is not a side for our triangle. So the description we're going to use for that is right here. It's neither. It's not a small triangle side and it's not a large triangle side. Investigating HE and AP, we already did that once. So HE was a small triangle side and then AP was a large triangle side. All right, we'll come back and do more with that in just a minute. We've got one more to fill out. So this last one, proportion C from up above, we looked at SE. That was a small triangle side on the right part of the picture. EP was one of those neither pieces. It wasn't a triangle side, it was just that little bottom section right here where that W was. Going back and looking, SH, well, that's the left side of the small triangle, so that's another small triangle side. And HA was another one of those neither pieces. It wasn't a side of the small triangle, but it wasn't a side of the large triangle either. So, question 3, what occurred that caused the false proportion? The false proportion was B. That one did not turn out to be two ratios that were equal. And the big reason why is right here in the denominators. Do you see how we weren't comparing things that were alike? Comparing one of those little neither segments to a side from the large triangle is what we call mismatching. There was mismatched parts, mismatched segments in that proportion. And anytime you incorrectly match segments in a proportion, you're not going to end up with something that's true. You're going to end up with something that's false. Question 4, did any of the true statements surprise you and why? So A and C were our true statements right over here. I wouldn't say that A is super surprising. This is what we learned in class 42. If I compare a small triangle side to a large triangle side, when those triangles are similar, any other small side and large sides should have the same ratio. So that's exactly what we learned based on the definition of similarity. However, part C here is surprising. They didn't compare sides of similar triangles. They compared this neither piece in the denominator both times. So this shows us that there's something different going on here. Proportion C has those neither pieces. We didn't use those. So I have somewhat of a question. What's going on here compared to what we learned with our similar triangles in class 42? All right, go ahead and flip the page, and I'll meet you back here to talk about what's happening with those neither pieces. All right, that proportion C is an example of our triangle proportionality theorem. So this theorem allows us to use those neither pieces, but only in very special circumstances. If you look back at this original picture, we didn't even talk about this before because we were given a similarity statement, but there was a clue on this picture that HE was parallel to AP. That is actually the hypothesis, the requirement part of the triangle proportionality theorem. So this says if a line is parallel to one side of a triangle. So in this picture, if this line right here is parallel to this side of the triangle, then something additional happens in terms of our similarity and the things that we can do to solve problems. What happens is that that parallel divides the other sides of the triangle proportionally. So when we're talking about the other sides, we're talking about this right here where that line intersects the left or the right side of that triangle, and this right here where that parallel intersects the left side of that triangle. And so what we're saying when those sides get divided proportionally is that this point and this point right here split these sides up. And so what we end up having along the left is an A and a B segment split by that parallel. And then on the right, we have a C and a D segment. And so what we're allowed to do when we have that parallel to a third side of the triangle is we're allowed to set up a proportion using that neither piece. In this proportion, that neither piece is up top, and then we have our small triangle side on the bottom. Same thing over here, that neither piece is on top, and then we have that small triangle side on the bottom. So we can set our proportion up that way, or we could flip it upside down, which is what we saw in the proportion on the front. We had the small triangle side on the top, so that would look like B over A with the neither piece on the bottom, and then this side would flip to correspond. Small triangle side would be D over C, the neither piece. What's really important for you to know, though, is that nothing in the triangle proportionality theorem talks about the parallel and the triangle side that it's parallel to factoring into this proportion. So we cannot use this theorem if our goal is to find E, the line that passes through, or F, the side that it's parallel to. We have to solve for those using our triangle similarity.